Okay, so we are going to start stream very soon. Um, Welcome. Oh, let's not have an echo of me. Um, Welcome. All right. Yes, echo was not intended. All right, cool. Let's just go for it. That seems like a good time. So basically, I'm going to be making a worksheet. If you're interested in the topic of the worksheet, that's great. You can ask me questions about it. Um, if you have questions of your own about, I think I could probably do up to Calc 1 or maybe Calc 2. I might be able to help you with undergrad math, but that was like more than 10 years ago, more than 20 years ago, maybe even. Yeah, about 18. I don't know if I remember any of it. So I'll try to help, but there's a huge probability that, or a high probability that I might not be able to help at all. Okay, so my worksheet today is on a very old problem, a problem that is easily solved in calculus, but we can prove that it works in algebra. So that's why I have the algebra and calculus tags, making sort of a sketch of the worksheet here. I don't know if you'll be able to see this, but I hope so. I'm sorry I did not put makeup on my hand today. So, anyway, voila, a piece of paper and webcam above it, obviously. Uh, yeah, so I'll be working today on my worksheet unless someone has comments or questions. And yeah, that's the way today's stream is going to start out. So the question today is very, very much classic. We have 40, let's say meters, just to be nice to everybody in America. We have 40 meters of fencing. Um, and the question is, if you're going to make a rectangle out of this 40 meters of fencing, what is the optimal way to maximize the area? So, uh, so this and I think most people who know math probably know what the answer is here. But can you prove it? Can you prove it using only algebra? And that's the goal today. So this is the first question we're going to do. The next question we're going to do is something I actually haven't looked at. I know the answer only from calculus, but I'm trying to figure out if I can make a way or find a way to explain it with only algebra. Same, well, yeah, same 40 meters of fencing, but this time there's a river that you can use to fence off one side. And I believe the answer is this side is 20 and this side is 10. But can you prove it with only algebra? This one I've actually done before. I know what the answer is. I know what the process to get to the answer is using only algebra. This one requires probably a bit of study. So that's where I'm going with this today. Feel free to ask questions. Okay, so yeah. So the answer here is a square. As you might know, you want to make a 10 by 10 square. The perimeter is 40. The area is 100 meters squared. So this part I've done. This part we'll work on it later. Hopefully it'll pan out. But let's see. Yeah. Okay. So this is the answer. How do you prove that's the answer using only algebra? Well, one way to do that is to say that we have a square. Let's say we know it's 100 meters squared as far as area. We know the sides are 10 by 10. So assuming this is the answer, can we prove it's the answer? Which is very different from coming up with the answer. I agree, as we know. So what we're going to try to do here is to see if we can make it a different rectangular shape. And this one would be 10 plus a. This is 10 minus a. So that the perimeter is again 40. And all we have to do is show that if a is not 0, then the area will be smaller. Okay. Actually, that was probably a bad choice of variables here. Let's make it a b. That was a b. Pretend. So, yeah. So the area here is 10 plus b times 10 minus b. That's equal to 100 minus b squared. Difference of two squares. And we can see if b is anything other than 0, the area is less than 100. And so we conclude that the best possible area is in fact 100. Because if you try to deviate from the square, you end up with less area. That's basically the proof. Okay. So I'm just doing, I'm thinking through this problem today. So that's that. All right. Just to make sure, let's do the calculus to figure out if this is actually right. Let's see. We have, what is this? So perimeter, or not perimeter, but the total length equals width times 2 h, let's say. And the area is equal to HW. So this one gives us 40 equals W plus 2H. So W equals 40 minus 2H. Okay, so area equals 40 minus 2H times H. Kind of swap those, but anyway. And we have to maximize this area, so we take a derivative, a prime equals, let's do product rule just for fun, minus 2H plus, so that's this times the derivative of this. Now we have to have this times the derivative of that. Negative 2 times H, I think that's right. So a prime equals 40 minus 4H, and we get that H equals 10. Okay. So if H equals 10, W equals 20. All right, so one side's 20, one side's 10. To be more accurate, or more specific, H is the side that has 2 of them. All right, let's see if we can prove this with just algebra, which is possibly interesting. All right. All right. So let's see. We have our setup. This is a 20. This is a 10. This is a 10. Okay. And then what happens when we make this length shorter? Okay. So then the width in this case, which I mislabeled in the variables, The width is 20. Well, let's make it 20 minus 2k. And the height is equal to 10 plus k. And I believe that preserves the 40. Okay, so let's see what happens. I don't know if this is possible, but we'll try. The area equals WH. This is equal to 200. Oh dear. Okay, 200 minus 20 plus 20. Well, that works out. Minus 2k squared. So, yeah. We have the area equals 200 minus 2k squared. Whenever we change k to be some positive number, the most area you can have, if this is the formula for area, is 200. And guess what? We get k equals 0. So yeah, so that was nice. Let's see. Yeah, okay, that's fine. That was actually a lot slicker and faster than expected. Okay, let's do another calculus problem. Let's see if we can simplify it. We can prove it in algebra. Let's try the square becomes a box problem. So, yeah, I agree. Hello, Dr. Meanfield. How's it going? Right. That's the point. That is the point. That you don't need to know derivatives to figure out the answer. So we knocked out both of those pretty quickly, actually. Kind of surprised at the second one. I thought it was going to be more complicated. You have a 10 by 10 sheet. You're going to cut out x here, x here. This is an old calculus problem also. Let's see if we can do this by knowing the answer and proving that the answer is maximal. So using calculus, the base of the box will be 10 minus 2x. We'll need 2 of those, and then we'll have to multiply by x. So the volume here is this. Let's put like a divider here. Yeah, okay, so that's the volume. Let's maximize it. Should I actually try to do a triple product rule? I think not. I think we should just multiply it out. Let's see. So this is 4x squared. I'm gonna mess this up. Minus 40x plus 100 times x. I'm saying that with completing the square in the first two problems, for its quadratic function to be optimized over, you don't even need to know the answer first. Would you like to expand on that? I'll be happy to entertain this. I don't know exactly what you mean. I think that, let me just be clear. Oh, completing the square. I see. Okay. I understand. Okay. So you're saying that if we have an area function that is, let's say, 10 minus w times w, all you need to do is find the apex of the parabola, right? fair enough. Um, and you're saying you would prove that by completing the square, which is fair. Okay. That's fair. No. Okay. I think I'm using something possibly more basic than that by just saying squares have to be zero or positive. So if you have an object, sorry, a square less than an object, the only way for the whole expression to be minimal is if the square is zero. But okay, no, I agree. I agree. You can do it that way. Um, yeah, no, that's fair. Um, yeah, okay, okay. I agree. I agree. Let's try this one. This one looks like it might be more complicated. I understand. I understand you're looking for the. I'm guessing you're looking for the apex using the completing the squares method, right? Or the vertex. I'm not using conic sections here, but okay. So, um, okay. So just to sort of say this, and my deal is that when you have an equation that or a formula or sorry an expression that looks like this, like you can only maximize it when b zero. That's all I'm saying. So I think it's more natural to just say that a square is at least zero, and subtracting a square can be maximized by making the square zero. So that's what I'm trying to get at. By the way, welcome and thank you for your comments. Yeah. Um. Yeah. So so I think we agree. We're good. Okay. Let's see if we can do this one by finding out the answer using calculus and then doing the sort of uh, the arguing that the square or maybe some square times a constant maybe that's my guess here is going to be or is going to give us the minimal amount of volume. So or the maximal or minimal. Let's try maximal. Yeah, let's try that. Sorry. So I've forgotten the answer to this one, which I probably should know because it's such a classic problem. But let's find V. I want to mess up on the arithmetic or algebra here, I'm sure. Yeah. Hmm. Okay, let's take a derivative. Okay, set equals 0. Let's divide everything by 4 just because it's nice. Oh boy. Let's hope it's a good answer. Oh, haha. You can use a cool trick here. Um, Basically, what I'm doing is this, where y equals 5. Let's solve this thing. Um, oh, oops. Haha. I can't factor 3 apparently. Let's see. Yeah, this looks like a minus y and a minus y here. So, checking my work right now because I feel like I probably messed something up. Let's see. Yeah, okay. I'm getting stuck on a quadratic. Ugh. Okay, so this one's out because that makes the side 0. Wow, fraction. Not good. That's okay though. So x equals 5 over 3 is what the answer is. Okay. So let's make x 5 over 3 and see if our kind of trick works again. Can you see stuff in the shadows? Okay, good. All right, so 5 over 3 is 2.66. Okay, so that seems reasonable, I suppose. All right, so the base right now is wow, I should have picked a better number than 10, but that's okay. The base right now is 10 minus 2 5 over 3s, so it's 30 minus 10, 20 over 3. And then the height is 5 over 3. And let's just check our work. I'm going to calculate it for x equals 5 over 3, the volume, and then I'm going to go back and try another value and see if this is actually greater. So we're checking our work for the calculus so far, and I am going to try to then do the algebra proof instead of relying on the calculus. So okay, so we have this thing. We get squared, I think, right? Yeah. Okay. 400 over 9 times 5 over 3. Yeah, so that would be 800 over 27. Okay. 800 over 27. Did I do that right? Ugh, did I mess that up? I think I did. Ugh, I am so not in it right now. Let's see. 2,000 maybe over 27. Let's try that. Yeah, okay. So, man, I'm really tempted to come back here and change the 10 to like a 30. Let's just do that. Let's start this over. Well, all right, whatever. All right, so that's that. All right. So let's try something that's close to 5 over 3, but not exactly 5 over 3. We'll use decimals. 5 over 3 is 1.6, I want to say. And so let's use 1.6 repeating. Let's use 1.6. So x approximately equals 1.6. We have here 10 minus 2 of those. That'll be 3.2, so it's 6.8, I want to say, squared times 1.6. I don't know how I'm going to compare these later. I have it over 27. To get out a calculator. All right, anyway. Well, actually, there are ways to compare them, but still. Wow, I'm giving myself a headache. Yeah, I'm just going to use a calculator. Don't care. I apologize for using a calculator to the purest of the math majors. Let's see. So, just to check, 1.6. Let's check everything here. Yeah, okay. So 1.6 times 2 is 3.2. Yep. Minus 10, 6.8. Okay. And the other side is 1.6. Okay, cool. So, ow. Oops, sorry, noise. 6.8 squared 73, almost 4. Oops, I can't write. 73.984. Okay. Let's try to figure out what 2,000 over 27 is. 74 point a bit more. Okay. Okay, so we changed the numbers a bit. We got a little bit less. That's a good sign. If I were a better mathematician or a better checker, I would also try 1.7 and see if we get, well, let's just do it. Okay. So 1.7, 3.4, 6.6 squared times 1.7. Let's try that. $74.052. Oh, that's not good. Did I do that right? 3.4. Yeah, it should be fine. Okay, let's. Oops. What's 2,000 over that thing again? 27. 74.07. Okay, so that's cool. Yay. So probably right. All right, let's try to do it with the algebra method. All right. Wow. Okay. So let's put the side of the square as I don't know, d. Side of the square is d, and we found out that it should be where'd it go? 5 over 3. Oh wait, no, that's x. D is 10 minus 5 over 3. Just 20 over 3. I have it written down right in front of me and I can't see it. Okay. And then we have 5 over 3 here. Quick check. Yeah, they add up to 30 over 3. That's 10. We're good. Bit slow here today. So we want we can take away from drx. I wonder if that's going to change the problem. We could probably do both because, we'll see. So let's do that. So for each part of this we take out, this is 20 over 3 minus 2 difference, which we'll call SAT. And this one will increase by t. Wow, this looks like a not fun thing to multiply together, but we do what we do. Okay. Yikes. So we need d squared times x, which is probably not a good bunch of variables considering dx is a derivative, but whatever. Wow. Let's see. 4t squared minus 4080 over 3t. I feel like going to Wolfram now. 400 over 9 times 5 over 3 plus t. Okay. Okay. So, this is the constant term first, which I almost messed up before. Oops. And now I have messed up again. Let's see. 409 minus 409. Well, that's good. Okay, so those cancel. Yeah, okay, these cancel. So that's the t term. Let's go for the t squared term. That's going to be 80 over 3 t squared minus this one isn't going to be as nice as the square one. Let's see. So we get 3 plus 20 over 3. Ouch. Okay, and then let's see. Yep, plus 4t cubed. Okay. Um, Nothing sticks out to me as something to quickly tell if we can maximize or minimize t here. Yeah, I don't think this is going to work. At least not without some more thinking and possibly a nice trick. Maybe we've hit a dead end. Okay. Let's see. And just to check, let's well, negative 80t squared plus negative 80t squared over 3 plus 20t squared over 3. Yeah. So, what I want to say here... Oh, wait. Oh. Okay, so we want to show that here t equals 0 is the best that we can do. Well, I mean, if t equals 0, then the thing is 0. Wow, can we prove that this is always negative around t equals 0? Seems interesting. Let's try t squared times, what is this? T minus, sorry, 4t minus 60 over 3. So around t equals 0, this bunch of stuff is definitely negative. And this bunch of stuff is definitely 0 or positive. So that means, I think, that t equals 0 is actually a point where we get some kind of minimum for this entire expression. Yeah. Okay. So yeah, I think we can say that. I think that's a valid statement. That this may not be the only answer, but it's well, uniqueness of answer. Feel free to chime in if you're out there. This is something I haven't done yet, so we'll see where the logic goes. Hopefully, the logic will go well. Okay, so let's look at the bounds here on 14 minus 60 over 3. If 4t minus 60 over 3 is always negative for all possible values of t, then we can say that the t squared is definitely, like, t squared is 0 or positive, and the whole thing has to be negative or 0. And then we have our argument. So let's look at this. T squared minus 60 over 3. So the question is, when is this, for values of t, is this, or, yeah, so, okay. Yeah, so for what values of t is this whole thing negative? So we want to know when this whole thing is below 0. Yeah, t is less than 15 over 3, I want to say. Where did I get 60 over 3 anyway? Because that cancels nicely. 15 over 3 or 5. Oh, goodness. Okay, hold on. 20 over 3, negative 60. Okay, so this should be a 20 anyway. So, okay, t is less than 5. So that's the whole domain for t, I think. You can't make... Oh, but what if t is negative? If t is negative, it's still negative. Okay. So if t is less than 5, then, yeah, the argument holds. That's nice. Okay, cool. Wow, that's a lot more complicated than the other one. Partially because I had so many fractions, but anyway. That's an interesting thing. All right. Let's let's try to formulate this problem better so that we don't have so many fractions. Um, so let's redo the whole problem with better numbers, basically. I think each side being 6 might help. So let's write that out. So we have a 6 by 6 by 6, or not, sorry, 6 by 6 piece of paper. We're going to cut out an X here and an X here. In theory, we want 1 and 1, I think. So the base is a square of side d equals 4, and the height is equal to 1. And that gives us volume equal to 16 units cubed. And let's see if we can set up the thing the same way. So if we take d equals 4 minus 2t, and we take h equals 1 plus t, and we find the volume, what do we get? Okay, 4t squared. Let's say 16t plus 16. Okay, times t plus 1. All right. All right. Yeah, okay. So here's the volume. Let's multiply it out. This is 4t cubed. Let's see. 4t cubed. Thank you, Bud 64 for the follow. I hope you're enjoying this. All right. Me fumbling through some algebra here. All right. So anyway, so 4t cubed. This is t squared. This is negative 16t squared plus 4t squared. So that's minus 12t squared. Then we have some things that cancel, which is always nice. And then we have plus 16. So that's the volume. All right, cool. Can we argue that t equals 0 is the maximal thing that you can put here? So we got the 16 we wanted. That's here. And I have to argue that this is, this expression is maximally 0 for all possible values of t. Okay, so let's factor it. T squared times 4t minus 12. And 4t minus 12. Okay, so I want to show that 4t minus 12 is negative for all the t's that really can be there. So t is less than 3. Is that okay? Can t be less than 3? Yeah, because the side is 6. Welcome both of you. Please enjoy the stream. So yeah. Someone's doing fireworks outside. Anyway, so t is less than 3. And yeah, I think we're good here. This is negative for t less than 3. This is positive or 0. So altogether, the most we can get is 0 here. And we have maximized the area of this this shape. Sorry, the volume. Sorry. We've maximized the volume of the shape at 16. And there we go. Nice. Units cubed. Yeah, okay, so it worked. Wow. Kind of nice. Let me think. Is there any other calculus problem that's even worse than that one? Oh, we've been here for almost an hour. Wow. We've only done 3 problems. Okay. Actually, let's see. Where's my calculus book? I wonder if I can... Anyway. Let's see. What else can we do? maybe we can do a what do you call it? Well, probably not. All right, all right. So let's just kind of go over what happened today. Thanks, guys, for being an audience. Um, but yeah, so we started out with this. We started out with a. We did three classical problems today, or classic problems today. Um, what happened to the first one? I'm so confused now. All right, I'm just gonna go through it on a new sheet of paper then. All right. Anyway, so we had our first problem, which is you have 40 meters of fencing, and you want to make the best rectangle area-wise, the most area anyway. And this is a simple problem, and yes, even algebra. Calculus can solve it too. My solution here, or my proof here, was let's say that I just pretend that 10 is the best you can do. I'm yeah, so 10 is the best you can do. What I'm going to do is the area of the rectangle will equal 10 plus a sliver, 10 minus a sliver, if it is not exactly 10 on both sides. So we get that. We have the wonderful difference of two squares here. And it turns out if we add anything to 10, we have to subtract it from the other side. And the area ends up being 10 minus whatever we added or subtracted squared. This is definitely maximal when what we add or subtract is 0. So I conclude then that the best area we can have is 100. And that was the first problem. Let's see if I can do the second problem equally quickly. So this is just like a sort of a recap. So the second problem was the same type of thing, except we have a river. It turns out that if you have 40 feet of fencing, you want 10 here, 20 here, and 10 here, without giving reasons as to why that is. But once we have that solution, we can figure out if it's the optimal solution. We have A equals length times width. Let's make this the length. So A equals L. Oops, messed up. Can't write. A equals L minus 2 of the difference times W plus the difference. So if I take this side 10, blah, blah, blah. I messed up. Not a day here. I apologize, guys. So yeah, if I take the long side and subtract 2 times something, I have to take the other side and add the something. So the area total is this, assuming that I knew the answer was 10 and 20. And you multiply it out. Uh, 200 minus 2d squared. So now we've proven that if we change the 2010 sort of answer that we have, we get this extra term that is based on how much we took away from the 20 or added to the 20, because technically it's could be negative. But anyway, we have this extra term, and the extra term is maximized when d equals 0. So that means 200 is in fact our answer, and in 20s and 10s. So yeah. So we have a welcome too many cooks. Let's see. X times 20 minus X. Okay. Yeah, I understand. I understand, buddy, but I just need to know for this one, not like the vertex of the parabola or the formula for the vertex. All I need to know is that a square is 0 or greater. And if I just know that, then I can say this term has to be 0. So that means the difference between this, or sorry, any deviation from this will give us a lesser area. Oh. Okay. Yeah. Okay. So, see. Okay. So, yeah. But I have here 100 minus d squared. And it's, again, you just have to say that d squared is 0 or greater. So that means you don't want to deviate from the 10 by 10. So I understand that you guys know parabolas and probably even hyperbolas or hyperbolic sine and stuff like that. But for, for the problem here, I think it's a very nice sort of explanation. If you can just say that this is definitely 0 or greater, when you subtract it, you want it to be 0. So that means the two sides are 10 plus 0 and 10 minus 0. But yes, I know about parabolas. Okay. Um, and I'm sure you guys know about a lot more than that. But I'm trying to make a worksheet where like you can do sort of, well, you can solve a theoretically calculus problem with only algebra, and that's my goal here. Trying to trying to do the low hanging fruit in calculus using algebra. That's what I'm trying to do here. But anyway, all right. Okay, so the last one we did. Oh, this is a pain. All right, but the last one we did was this. We have a 6x6 piece of cardboard. We want to cut off parts of it. This is a classic calculus problem, and I claim that x equals 1 maximizes the volume after you fold it up. Okay, so that means the base side is a 4 and the height is a 1. So if we subtract from the base side, or add to the base side, 2 times d, and we add to this one 1 plus d, we can prove that the best thing you can do is to make d 0, and you will get the volume that is maximal. So let's try that. So this is 2d plus 4. Let's put the variables in front just because. This should be a square because this is the base side of the base. So we get, let's see, 4d squared plus 8d plus 16. Oops, did I mess up? I did mess up. Haha. Let's try 16 here. 16d plus 16 times d plus 1. And it turns out that we get 4d cubed. Oh dear. 16. Oops. Did I mess up? I did mess up. Okay. One of these has to be negative. Yeah, let's make this negative. We did the opposite way the other time. It doesn't matter though. It should be fine. Hopefully. Oh. Oops. Drat. Okay, I messed up. Hold on. Messed up my own problem. You can take the 4 here and add 2d, and take the x here and subtract d. Let's just do it that way. Let's just stick with that. Just to do something different, because you can get to the answer in several ways. Okay. Anyway, so I claim that 4 is the base and x equals 1. That's what I claim. Okay, I'm going to try to prove it using only algebra. So 4 plus 2 times the difference, and this is 1 minus the difference. So that's what I got now. And when you find the volume, you get 4 plus 2d times 1 minus d, and you get, let's see, 16 plus 16d plus d, 4d squared, times 1 minus d. Okay, so you get 16, that's fine. The d term cancels, you get plus 12, I think. Or was it? Minus. Let's try minus. Minus 12d squared plus, oops, minus, okay. 16 plus, no, what's wrong with me? Gosh. 16. Yeah. Minus 12d squared minus 4d cubed. All right, so if you multiply it out correctly, this is what you get. My argument is that this whole stuff is going to be negative unless d equals 0. And let's make the argument on the next page. So I have 16 minus d squared. Let's see, 12 plus 4d. Okay. So 12 plus 4d, that's positive as long as d is greater than negative 3, I'm going to say. So if d is greater than negative 3, this is positive. This is positive or 0. So we want d to be 0 to maximize this whole, or sorry, to maximize the whole thing. So I feel like my claim is correct, that the answer here is 16 units cubed. And that's kind of what I want to say there, hopefully. So yeah. So again, d is greater than negative 3 makes this part positive, and d has to be greater than negative 3 because we have a side of 4, and we can't deviate more than 3. Sorry, did I mess it up? Hold on. Yeah, sorry. We have a side of 1, and we can't deviate more than 3 away, I want to say. Something like that. It was more clear the other way. It was more clearer. Oh, good stuff. All right, so, yeah, I think that is what I've got for you guys today. Thanks for dropping by. Do you guys have any questions you want me to, like, talk about? I don't know if I can answer them, but I'll try. So yeah. All's quiet on the Western Front. No. Okay, so the volume is this. We're okay with this, right? Oh, okay. Yeah, the dimensions of the box are 4 on the base each side and a height of 1. That's what I contend is the answer. So what you can do here is subtract or add a little bit to this, to the 1, and you get 1 plus minus d. Technically, d can be negative. That's what we're allowing. If we subtract d from the x, we add or subtract 2d from the base. No. Oh, okay. The original cardboard, yes, is 6 by 6 area. And you want to take out corners and fold them. Here, let's just... this is... So you want to, like, cut out all the corners and fold them so that you get the maximal volume. But yes, the original flat piece of cardboard is 6 by 6. Yeah, this is the situation that the problem asks for. We're going to cut out these squares on all 4 corners, and the result will be a base of 6 minus 2x and a height equal to x. And so I contend that the 4 minus 2x is actually a 4. Okay, good. Yeah, we're good. Thank you. I would question my sanity over yours. So so when there's a mistake, there's a mistake. I'm totally admitting to that. Okay, so yeah, so that's how the proof goes. So you don't actually need to know any calculus to solve this problem, provided you know enough algebra and you know what the answer is, which is a little bit weird, but you know, that's the way this particular worksheet of logic is going to end up being. So yeah, I'm kind of surprised this one even worked, but it works, so we're good. All right, it's been an hour and 8 minutes. Let's see. Is there anything else I wanted to say about this? I think that's it. I think that's a good bunch of problems to put on a worksheet. Um, let's see. Oh, here's a fun one. This is just random. So I gave a few people this problem. X divided by x plus a is less than 1. And the question is like, what's a good way to solve this? Oh, that's a good point. I like the geometric way, although I'm not very good at geometry in general. But yeah, that's interesting. I will have to share this geometry thing that I came up with another day. But let's just do this because it's a short sort of exercise. So the normal way to do this is to move the one and then get the common denominators, and then do the. Hmm. Um. Maybe. Maybe. Oh, we could do that. Let's think about that. This is tabled for a while. Okay. So you're saying you want to make a cube. So if this is 6, and we want to make a cube, we'll have to have 6 minus 2x. Oh, well, part of the thing is that, like, you don't have a top for the cube. Okay. Yeah, we don't have a top for this for this problem. It's just the box. So that's part of it, and that might actually that might be the reason why the cube is why we have the answer we have instead of the cube. But anyway, okay. Anyway, here's another fun algebra problem. We're just I. So yeah, can you solve this one? This is a fun one. So the classical way to do this, the let's do it the right way that you're supposed to use in I guess algebra 2. You move the 1 over, you get x over x. X plus a, and then you have to subtract x plus a over x plus a, and that's less than 0. And that means you get negative a over x plus a is less than 0. And then you have to find the roots. Okay, well, the roots here are x equals a. The roots of the denominator and the numerator, so there's no roots of the numerator, so the denominator is x equals a. Oh, sorry, negative a. My bad. And then you do the number line, and you put a negative a here, and you're like, well, okay, so what makes this true? So when x equals, let's say 0, let's just test 0. Well, 0 could be on either side of this, but the point is that there's an easier way. Okay, so really quickly, let's go through the sort of shortcut way. So yeah, you have x over x plus a is less than 1. That's the original problem. And I contend we can multiply both sides by a positive and still have the thing be okay. So what I'm going to do here is not multiply by x plus a, because x plus a could be negative. We're going to multiply by the square of x plus a here. Oops, and I can't write. And we get this. And also we technically have to make sure the bottom's not 0. So we also have to add the stipulation that x does not equal negative a. So as long as x does equal negative a, we can multiply both sides by the square. And it's also obvious that x does equal negative a because it's in the denominator. So this is in the denominator, so we can't have that anyway. So let's see what happens. So we got x squared here plus ax less than x squared plus 2ax plus a squared. And we just cancel stuff. So a squared negative less than ax. I have not divided by anything. That, I hope. Oh. Okay, so there's a slight problem here. Because technically you have to divide by a, and if a is negative, then the sign swaps. Okay. I got caught on the last step. That's bad. Yikes. How do I get around this? Oh, okay. So, if a is greater than 0, x is greater than negative a, and if a is less than 0, then blah blah blah. Okay, so that's that. Okay. Oh, I feel bad. All right, so a is less than 0. X is less than negative a. I'm gonna say here. But anyway, the multiply by the square thing is a really cool thing, I think. So that's a little problem that came up. It's obviously nicer when a is actually a number, so you don't have to do the qualification at the end. But yeah, this is kind of a nice problem anyway. All right, so that's that. All right, anybody else want to be entertained by math? I'm pretty happy with this first episode. We got some people in here. That's nice, very nice. So hey, buddy, what is your background in math? Are you a really math person? Are you like a computer science or physics person? Or like what kind of what kind of flavor of math are you? So personally, I'm in. I have a math degree and currently using it to tutor right now. Um, I've taught community college for a while, um, but currently tutoring, just having some very open scheduling, and so yeah, that's me. Hi, Misi. What should I call you, Misi Jidi? Don't know what this is. Sorry. Oh, you're currently a math major. What level? Or what year? Or what are you taking? By the way, is there anything wrong with the sound? Because this is literally the first episode that I've had like lots of people in here. So hopefully someone will complain about the sound. If oh wow, real analysis is a pain. Okay. Thank you for the confirmation. Yeah, real analysis is pretty strenuous usually. Oh, that's good. That's good. Wait till you get to the graduate version. You'll have sigma algebras and stuff like that, which I don't know anything about anymore. But I just know there's a word like that. How's discrete math? Like, what are you learning there? And have you taken algebra, which is the other main thing that you have to take? Ah, nice. Um, yeah, combinatorics is cool. I Have you gotten to the point where you have? This is probably not in that class, but part of combinatorics, one part of it is you can convert a recursive formula in some cases to an explicit formula, and that part I think is really cool. It technically has to do with sort of kind of partial differential equations or something like that, or I don't know. Yeah, abstract algebra, fun stuff. Yeah. Um, you get to learn all sorts of fun stuff in abstract algebra. Like, have you ever tried to take powers of? Oh, I see. I see. Uh, so like basic number theory is very well, not always, but there's a lot of it that's integrated into abstract algebra. Um, so like if you take your digits. By the way, tell me if you have to go. I don't want to. I'm having fun, but yeah, you take your basic digits and start taking powers of them. You'll notice patterns. So this is a 0 and a 0 and a 0. So that's that. This is 1 1 1 1. This is 4 8 16 32 64 64 128 236. Okay. 3 is a 9, and then a 7, and then a 1, and then a 9, and then a... Oops, did I mess that up? Oh, let's try a 3. Sorry. 3, 9, 7, 1. 4 is 16 times 64 is 4. 6, 4, 6, 4. 5 is your... Well, everything ends in 5. These are just the last digits, obviously. Sorry, I didn't say that, but hopefully that was... That's okay. Okay, so bunch of 6s, 7. 7 is 49. 49 times 7 is 60. Sorry. 49 times 7 is 303 times 7 is 1. And then 7 again, and then 9, and then 3, and then 1. I'm making a huge mess out of paper. 2 here. What's the next thing? 8 times 2, 2, 8, 16. 8, 48. Wait, I messed up. 6 times 8. Wait. Okay, I messed up somewhere. Hold on. Oh, 8 times 8 is 64. Let's try that. Alright, so 2. 2, 8, 16, 6, 8, 6. Okay, yeah. Okay. And this one is 1, 9, 1, 9, 1, 9, 1. Okay. Oops. So my question is, yes, it should be 4. I apologize. But my question is, have you noticed the number of numbers it takes to repeat? It's either there's 1 and then it repeats, so that's these 2. There's 4, then it repeats. There's 2, then it repeats. Let's see. Okay. But the question is why? Why do these always repeat and they're all factors of 4? Like 4 seems like to not have much to do with the base 10 system, right? 10. It should be 5 or 2 or 1 or. But yeah, so a different question of why shouldn't it be 4? Why should all of these divide 4? And that's something you get to mess around with in abstract algebra. Yeah. 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 Why? Yeah. It has to do with, it sort of has to do with Lagrange's theorem, if I'm not mistaken. I'm kind of not sure if I should say what I want to say, because I'm not sure it's absolutely correct. But, yeah. Lagrange's theorem. It says that if you have a... Well, anyway, you'll see. Basically, if you have a group and... it is from group theory. So it turns out that that's a lot of paper. It turns out that 1, 3, 7, and 9 are the only numbers that are relatively prime to 10, which is the base. And this will end up forming a group. And because this is a group, every element in the group has to have a repetition that is a factor of the number of things in the group. It has to do with that. So, because these are the only ones that are relatively prime, and it's called U10 or 10U. Oh, I'm getting even more murky here. But anyway, point is that we have 10 things. There's 4 things in the 10 that are relatively prime. So within these 4, every single element has to repeat a factor of the number of elements there. And because of that, if you take this thing and multiply it by 2, you get your you get your other stuff. But anyway, let's not go there. It has to do with that. So I think it's called Lagrange's theorem. I'm pretty sure. This is what happens when you start talking about stuff you don't know about. Okay. Like I learned this, but that was a long time ago. Anyway. So another example is like, let's say 5. So instead of 10, let's look at 5. We have 5 numbers, mod 5. But only 4 of these numbers are relatively prime to 5. And it turns out that powers of these numbers, mod 5, will always give you, powers of numbers mod 5 will always repeat every 4, which means they can't repeat every 3, but they could repeat every 2 or 1. And that's kind of like the sort of application of a very cool theorem in abstract algebra. So, yeah. Let's see. So that's that. Interesting stuff. Yeah. Anything else anybody wants to know about? I'm glad you're a math major. There's not enough of us, and I wish there were enough of us that we could get some more math majors in like the K through 6 educational systems or parts of the educational systems. That would be really nice to have people that are like really excited about math teaching, say, 2nd or 3rd grade. But anyway, so that's that. I did, but again, it's been a while, and I barely got through grad school for health reasons, and so I don't remember much about the classes or really about the subject matter. So yeah, if I went back and looked at it, I think I would probably understand it a lot better. Probably, well, I mean, maybe I'll do that. Maybe I should do that. But yeah, I went through a master's program and got a bit sick, and so kind of eked out at the end. And if you guys want to stay for a little while longer, I'll happily share like the first part of my sort of the prelude to my thesis, which isn't very mathy, but it's kind of cool. Oh wow. Currently it's math education for K through 12, namely 7 through 12 though. Okay, all right, we can do that. So we all know this sequence. This is what I've pretty much heard. So this is Fibonacci with a capital F. You can also have Fibonacci with the lowercase f, and what that is just pick 2 numbers and then have the same pattern. So pick 2 numbers. Any 2 between -5 and 5. 3 and 5. Okay. Well, that gives us Fibonacci, but shifted. So let's pick some like non-Fibonacci numbers. And negatives are fine too. So don't go too crazy. Don't make me do pi's and e's and cosh 1 or whatever. But just, yeah, some numbers. Okay. Well, okay, that's fine. That's actually not what I'm gonna go for, but Cooks, you were probably right about that. Okay. -1, -1, -2. -3. Okay, so we get some terms and we get some like sort of a negative Fibonacci sequence, which is fine. Just checking my work here. Yeah, okay. Pick two other numbers. We need two more. We need two lowercase Fibonacci sequences. Or, I mean, I'll pick if you want me to, but I'll give you the. Okay, sure. Cooks, any ideas here? Any numbers that you like? Don't do like 15 over 37. -2 and 4. Okay. This is quite interesting. Okay. So, did I get this top one right? Did I get the bottom one right so far? I'm not going to keep going on to infinity, obviously, but just kind of like, let's see if we get this. Let's see, 2, 6, 8, 14. Yeah, okay. All right, so we're good. What I'm going to tell you is that anytime you have two lowercase Fibonacci sequences, you can add them term-wise, and it's closed. So these two will give you a -1. These two will give you a 3. These two will give you a 2. These two will give you a negative, not a -5, but a 5. This one will give you a 7. This one will give you a 12. And yeah, they're closed, which is really nice. I don't know what kind of math background you have, Cooks, but you know that closure is a super important part of algebra. Or you might know, sorry. But yeah, closure is a super important part of algebra. And algebra is about taking a set of things and taking two things in them and adding them in a certain way, and then at least getting closure and other things out of it. And so, yeah, so that's kind of like the sort of a fluffy part of my... Does it form a field? Let me think. I don't think so. How restrictive is the structure? Okay, yeah. So we're using termwise addition, so that's the addition. It is, it's not just associative, it's commutative for obvious reasons. Definitely has an identity. 0, 0, 0, 0 is technically lowercase Fibonacci. So it has inverses. So yeah, this is a group, and it's a group of sequences, namely the lowercase Fibonacci sequences, and so that's the first part of it. It's got some structure like that, so it's a group, yeah. Okay. Hey physics, how you doing? Can I give shoutouts? How do you give shoutouts? I think part of the problem is I don't know how to do that. So multiplication would work, but he asked about a field, which is more specific or more sort of regulated than just multiplication. One way to multiply this is to take the first sequence and multiply by the second sequence's first element. So you take the whole first sequence and you multiply by actually any sequence, sorry, any element in the second sequence, as long as it's a specific element. But I mean, the easiest one is to pick is the first. So if you take any sequence like this, you multiply by the -2, you do have closure and some other properties. So yeah. / shout out. Okay, hold on. Unfortunately, I cannot I can't do that from one of my keyboards for some odd reason I don't know yet. But let me try. Let me make sure I spelled the name right. Oh. Let's try this. There you go. There's your shout out. Fun stuffs. Yeah, this is so to answer your question, Too Many Cooks, You can put a multiplication here, or and also you can have a multiplication. Okay. By the way, are any others of you streamers? I'll be happy to shout you out. Also, good to get some people in this chat to know who you are. Um, yeah. Another really cool thing in algebra is I kind of just went through everything that you need for a group. I'm not sure if I went through everything, but almost everything. Um, but associativity, closure, and inverses. I think that's everything. I'm a bit confused, but anyway, um, another really cool thing that forms a group are magic squares of any particular size. So if I take a magic square, uh, let's see, can I do this? I forgot how these things work. Um, I think 4 goes here and 6 goes here, maybe. Yeah, the identity is 0, 0, 0, 0, 0. That is true because that is also Fibonacci. You start with 2 zeros, you keep adding them through, and you get bunches of zeros. So yeah. Let's see, 15, 15. Oh, that won't work. Messed up. Anyway, point is that if you add two magic squares term-wise that are both the same size, you get a magic square, and it's closed. Um, and yeah, it's just nice. I'll check Wikipedia. Okay. But lots of really cool things form groups. A lot more than the ones that are taught in class. Um, so yeah. So how was your stream, physics? Just really quickly. Okay. Are you out there, physics still? Non-existent. Wikipedia's non-existent. Oh, you didn't have a stream today. I see. Oh, I didn't know that. Okay, that's cool. Sorry. um. So let's see. Anybody else want to make me talk about math? I see. I see. So yeah. Hey, buddy, if you have a math question about your undergrad math, I will try to research it and find out if I know the answer, but it's been a while, a long, long while. I'm more into the little algebra tricks here. So, yeah. Um, let's see. What else is there? Yeah. Oh, okay. Sure. Of course you are. All right. Okay. Um, yeah. Oh, identity. Sorry. Yes, that's important. I forgot identity. Oh well. Oh, I'm. Huh. Yeah, computers proving theorems is very interesting. I don't know much about it, but I know it's like hard. Yeah. And so yeah. Let's see what else is there. Uh, So should I give this problem? Ah, is there anything anybody specifically wants me to talk about? I'm just wondering. I'll try. Um, and if not, I might decide to call it a day. Oh no! I have to give a puzzle at the end of stream, especially the first one. Come on, right? All right. So I might have had I don't know if I told you about this one physics, but there's like a toothpick puzzle. So like this is a classic one. It only has this many toothpicks. The question. Okay, sure, buddy. Come back whenever you want. I'll start for the puzzle. Okay, quickly. Okay, so yeah, so you got this thing, and the question could be like, take away 4 toothpicks and leave 2 squares. And most people will try to do it by brute force, just kind of like, okay, well, and then they're like, oh well, these 4 leave 2 squares. Okay. 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 So there's actually a nice math way to do this, and I'll go over this next time. It'll probably be in the VOD, so even if you miss next time, just come back and I'll do this at the very beginning. Um, can you take away? So this has 2 puzzles surrounding it. One is take away 3 um, picks and leave 4 squares, and the other puzzle is take away 5 picks and leave 3 squares. And there's actually a nicer math way to do it than just brute force. But anyway, these are the 2 problems. So that's what I'll leave you guys with. Uh, Vector calculus, it's so practical. Okay. But yeah, so this is the puzzle here. And again, um, yeah, I'll do the answer at the very beginning next time. Okay. So I guess we'll see you later, buddy. Okay, try the puzzle. There's a nice math way to do it, but you know, see if you can figure it out either way. Yeah. Thank you for joining us, buddy. Thank you for joining us. Anybody else that's in chat? Thanks, physics. What kind of vector calculus do you want to do? Okay. So we're all good. We're all good. All right. Thanks, guys, for showing up. Thanks, guys, for watching. Uh, I don't think I want to raid today, so we're good. All right. I'll see you guys later. All right. Thanks again. All right. Goodbye, folks. Bye, cooks.